Okay, guys, this is a video to cover the instruction on Monday, December 19th, which is really the first part of your homework. You were instructed to do this tonight. And there were a lot of people that were out last week and people that were making up the quiz today, so missed this instruction. And additionally, I must have had 10, 12 absences throughout the day today. So this is specific, and it's a good review, I think, as well. But it's specifically a recap of what we did in class. I'll try to give you the quick version because I have to use sort of the clunky smartboard software. It's not going to look great, but hopefully it will at least help you. So we're going to start with sodium. You need a periodic table to do this. So I'm assuming that if you're going to go through this with me, have the periodic table in front of you right now. So go ahead and pause the video, get yourself a periodic table, preferably a red colored pencil, a blue colored pencil, and a regular pencil. Okay, so assuming you've gotten those things after pausing the video, we're going to go ahead and start. So we're going to start with sodium, which is element symbol Na. And again, this is not going to look great, but it is what it is. Its atomic number is 11. We find it on the periodic table because it's atomic number 11. We know it has 11 protons. Because it's got 11 protons, it has to have the same number of electrons. And we look for its mass. It's 22.99 something, so we're going to round that up to 23. Because this represents the total number of particles in the nucleus, meaning the total number of protons and neutrons, and we know 11 of those 23 are protons, what's left over are neutrons. To put it in a simpler way, 23 minus 11 equals 12. But the number we want to deal with right now is this 11, because the 11 electrons are what we have to place down here in this blank Bohr model. So I'm going to switch to blue and make my cursor a little bit bigger. And then what I'm going to do is I'm going to cross off the first two, and that 2 is going to become a 9, because I'm going to go 1, 2. I've placed the first 2 electrons from the 11. I have 9 left over. I can fit 8 in the second shell. So I go 1, 2, 3, 4, 5, 6, 7, 8. And notice these are inner electrons. We're drawing them blue. I'm going to switch to red. And again, probably have to, I have to adjust it again. I'm down to just the 1 electron. And because I can fit 8 in the third shell, but I have just 1 left over, I place it as a red valence electron. Anything in the outermost shell is a valence electron. So now we move on to the oxidation number. The oxidation number is, we're going to do the Lewis dot diagram first. So the Lewis dot diagram is simply rewriting the element symbol, and then we take the number of red electrons and we place them on the outside. And in this case, it's an alkali metal. It has just the 1 valence electron. Now, the trickiest part of all of this, the thing that that students have the most trouble with, and I'm trying to give you that leg up on high school chemistry when it comes around, is this concept of oxidation numbers. So first of all, you have to remember that the whole reason we're talking about this is because we're in the middle of chemical reactions. Whenever there's a chemical reaction, what that means is that there is sometimes covalent bonding, sometimes ionic bonding. Meaning elements are bonding together. They're changing, they're shifting, they're moving around and creating new substances. We are talking specifically about ionic bonding today and tomorrow, actually. And for grade level, we won't do any covalent bonding. We'll just do ionic bonding. And when we do ionic bonding, we're talking about the ionization of atoms. And what ionization means, like the Greek word ion, I-O-N, means to go. And the reason it's called that is because it's talking about electrons shifting. They're being transferred. They're either leaving an atom or they're going to another atom. So you're either gaining or losing. Because these electrons, when they become ionized for those nanoseconds, they are changing their properties. So when I look at sodium, sodium's an alkali metal. Sodium has 1 valence electron. It will move heaven and earth to get rid of that 1 electron so that it has the full shell underneath. And actually, it does it very easily because it's just got 1. It's one way to look at it is Is it easier for sodium to lose 1 electron or gain 7 to make a full shell? And the answer is it's easier for it to give 1 away. And so because it's going to transfer it away from the actual atom, that means that for that brief moment of ionization, the number of electrons go from 11, and it's neutral, down to 10. And because it's dropped a negative charge, because protons are positive and electrons are negative, it leaves the atom in that brief moment more positively charged. So because it's more positively charged, we write, well, first of all, we write 1, because the 1 electron is what's leaving sodium. And because it left and left me more positive than negative, we write a plus. Now it's tricky because you think plus, it must mean it's gaining 1. And is it positive 1? No, none of those things are the case. You have to think of this, number 1, in terms of how many electrons are being added to an atom or how many electrons are leaving the atom. In this case, 1 atom is leaving, and it is leaving the particle more positively charged. So that's sodium. Now let's look at fluorine. Now if I go to fluorine, and if I go to ptable.com, and we look up fluorine, fluorine on your own periodic table is element number 9, and it's got a mass of 18.9984. You can see it over here when I click on it. Okay, so let me go back to my screen here. Where am I? I'm over here. So I said it was element 9, right? So it's element F, which is element 9, and we know it's got a mass of 19. So that means it's got 9 protons, 9 electrons, but because it's got a total mass of 19, 9 of them are protons. What's left are electrons. Now, before I go any further, I want to remind you that at any point you can pause this, rewind it, go back, do whatever you need to do to make sure you understand it. I just told you a whole lot of information over here, and I want to make sure that you understand it. So here we are. We have 9 electrons we have to deal with. So we're going to switch to my blue. I'm going to make my cursor a little bit bigger, and I'm going to go from my 9, drop me to 7, because I'm going to place the max number in the first shell is, of course, 2, leaves me with 7. Now, I can fit 8 in the second shell, can't I? But I've only got 7 to place. So that means all 7 will fit in the second shell, and they all become valence electrons, which means they all are going to be red. 1, 2, 3, 4, 5, 6, 7. Now I go back to my Lewis dot diagram, and I have F. F has, fluorine I should say, has 7 valence electrons. We want to be symmetrical, so we're going to go 1, 2, 3, 4, 5, 6. Now there's 2 spots. It doesn't matter which one I choose. I'm going to go there. So actually, there, that looks better. So that's a fluorine dot diagram. So the simple question, actually simple to answer question, is it easier for fluorine to gain 1 to become a full shell or lose 7? And the answer is to gain 1. In fact, the halogens, which fluorine is a member of, that's the group 17 nonmetals, they're gases, the halogen gases, they love to react with the sodium and the lithiums and the other alkali metals, the ones that have 1. If you see, this little electron right here fits nicely right here. In fact, sodium fluoride is an element that we find in our toothpaste. We find it in, it's actually used, it's going to sound horrible, it's used in pesticides. It's used in all sorts of different compounds. And sodium fluoride works because sodium wants to bond, fluorine wants to bond, and so it also has 1, actually let me make this a little smaller. It also has 1 electron to deal with, so its oxidation number is 1, but it's gaining 1. So that brief moment of oxidation, that brief moment of ionization, means the electrons go up to 10. So because it goes from 9 to 10, it's gaining a negative charge, and it is more negative than positive, so its ionization is this. And this is a phenomenon, and you don't need to know this. The honors, I would like you to know the difference between an anion and a cation. So if you actually look this up, you can type in cation, okay? And a cation, by definition, is a positively charged ion, one that would be attached, oh, you don't need to know that part, but the positively charged ion is a cation, and an anion is a negatively charged particle. So again, back and forth, you can look at the spelling of each of these, cation and anion. That's how those are pronounced, by the way. And so we go back to where we were, and those are the first two that can kind of drive you through this particular activity. You know what I can do is I can do one more. I'll do the silicon. So silicon is, let's see, silicon is element, it's in the group carbon family. It is element number 14 with a mass of 28. So we'll go element number 14. It's got a mass of 28, which means these are all going to be 14s. Okay, and we write our silicon down here. Okay, we've got 14 electrons to deal with, and our 14 electrons will go first 1, 2, and we cross that to 12. 3, 4, 5, 6, 7, 8, 9, 10. We placed 8 more, which leaves us at 4. So that means I can fit all 4 in my outermost shell. 1, 2, 3, 4. Now, every element in the carbon family has 4 valence electrons. It's why they're in that family. So, is it easier for it to gain 4, or is it easier for it to lose 4? Well, silicon, carbon, and other members of this family, right here, germanium, tin, they tend, in fact, 9 times out of 10, they tend to share electrons. They are involved in covalent bonding, which means they bond and they are involved in chemical reactions, but they are not ionized. They don't get an electrical charge. And that's something for honors on Wednesday grade level. You don't need to worry about that. But I mention it only because, again, 90% of the time, you aren't even going to bother with an oxidation number. The word oxidation in this context means the number of electrons that are leaving or coming. And if it's not oxidizing, it doesn't matter. But there are times when it does involve itself in an ionic bond, and it is ionized. And most of those times, it's giving them away. And if it's giving them away, it leaves it more positively charged, because, of course, if it gave away 4 electrons, it would become more positively charged. Okay, so hopefully, folks, you've understood the lesson that we had today. This is the short version, of course, of what we did in class, and this represents a small portion of the homework that is ultimately due on Thursday. Of course, if you have additional questions, you come and see me, and hopefully I can help you out.